Good morning, dear friends. In today's lecture, we are going to start Unit 2 subgroup. In today's lecture, we will see what is the definition of subgroup. We already studied set, subset like that. So group and subgroup. So here we are going to study definition of subgroup and examples. In next lecture, we will study some theorems regarding subgroup, some properties like that. So let us start. Thank you. First we see the definition of subgroup. Let G star be a group and a non-empty subset EH of G is said to be subgroup. We already studied set, then subset. Similarly, we studied group. Now we will study subgroup. First condition is it should be subset of G. So H is said to be subgroup of G if S star, same binary operation, there is no difference. S star is itself a group. And we can write notation, or it is denoted by H is a subgroup of G, means H less than means sorry, this is the notation. Now we write examples. We already know if we take G as a set of integer means 1, 2, 3, 4 like that, and 0, minus 1, minus 2 like that. Star we can take as addition. So take H is equal to 2Z, that means set of even integers. So clearly H is a subset of G, and H star means H addition is itself a group. Why? Because it satisfies 4 property. Let me ask question, why? So answer is because it satisfies 4 conditions. First condition is, first of all, it should be non-empty. Here it is clearly it is non-empty. H not equal to phi. This is notation of phi, non-empty. Closure property satisfied. What is closure property? If you take any two elements from 2Z, means H, then clearly it implies A plus B, plus is binary operation, belongs to 2Z, because addition of two even numbers is again even. You can take 4 plus 6, 10, it is even. 6 plus 12, 18, that is even. Addition of two even integers is even integer. Second property is associative. Clearly, if we take three even integers, say ABC, then A plus B plus C, that is same as A plus B plus C. This is true for all ABC belongs to 2Z. So in this way, if we take, we can try 2 plus 4 plus 8 like that. 4 plus 8 is 12. 2 plus 12 is 14. Same answer we will get. 2 plus 4, 6. 6 plus 8, 14. Like that. Third is existence of identity. Means there exists, this is symbol of there exists. There exists E belongs to 2Z, means EH, such that A plus E is equal to A, or all A belongs to 2Z. How we have to find? Just check. Just take any value, any element from 2Z, say 6. 6 plus E equal to 6. When it will be possible? If E equal to 0. And 0 belongs to 2Z, that is even integer, that belongs to 2Z. So there exists E equal to 0, that is element of 2Z, which work as a identity element. Instead of 6, you can take 16, 8, minus 6, minus 9, sorry, minus 4, like that. Then you will get the property A plus E equal to A and E equal to 0. So 0 work as identity element. In short, we can write like this. Last property is existence of inverse. That means for A belongs to 2Z, there exists B belongs to 2Z such that A plus B equal to E. Means here for any E is important. For any A belongs to 2Z. Here E already find E equal to 0 from third. So B equal to minus A. For all A belongs to 2Z. That means inverse of say 6, there exists minus 6 such that it is equal to 0. If you take minus 8, there exists plus 8 and that is equal to 0. That means 6 inverse is equal to minus 6. Here that means minus 8 inverse is equal to 8. Under addition, star is equal to what is given, addition is given, binary option. This is true for all A. For each element there exists inverse. So inverse property is satisfied. So in this way, so from 1 to 4 we get 2Z plus is subgroup, is group first of all. And so 2Z plus is subgroup of Z plus, because 2Z is a subset of Z. Z is a set of integer. 2Z is a set of even integer. In general, note NZ is subgroup of Z. Second is say 6Z or say 16Z is a subgroup of 8Z. 8Z is subgroup of 4Z and 4Z is a subgroup of 2Z and 2Z we know 2Z is a subgroup of Z. That means 16Z is also subgroup of Z also. Now we take non-examples. Non-example is also important. So if we take G star equal to Z plus, that means set of integers, that means 0, 1, 2, dash dash dash. Here -1, -2, -3, dash dash. And if we take say k is equal to set of odd integers, that means 1, 3, 5, 7, dash dash dash. Here also -1, -3, -5, dash dash dash. K is a subset of Z clearly, but K is not subgroup of Z. Why? So it does not satisfy at least one of the property from 4. Means it may not satisfy closure, associative, or existence of identity, or existence of image. Let us check, because if we try for closure property, 1 and 3 belongs to K. So 1 plus 3 equal to 4 does not belong to K. 4 is not in the set of odd integer. 4 is even integer, not odd integer. 4 is even. So closure property doesn't satisfy. Can you tell any reason, any other reason? First cause is closure property not satisfied. Second, if we discuss about existence of identity, 0 is not present. Identity does not exist. First reason is this is. And second is identity property. Identity element does not hold, does not present. Identity property does not satisfy. In K means E is equal to 0 and does not belong to K. Two reason is sufficient. Now let us discuss some remark. E and G are always subgroup, and they are called trivial subgroup. Second is if G is group under Hadoop operation binary star operations. H is a subgroup of G, K is a subgroup of H, E implies K is a subgroup of G also. It satisfies transistor. In next lecture, we will take some theorems on this criteria to be subgroup. Thanks for listening patiently. Now, dear friends, let us discuss some theorems on subgroup. Theorem 1. A non-empty subset H of group G is a subgroup of G. In short, we can write like this. If and only if. Meaning of this is if and only if AB belongs to H implies AB inverse belongs to H. Means this is the criteria to be subgroup. If we take any two element in H and if we take the product like this A into B inverse, here whenever we are going to take the theorems, we by default we can take binary operation as a multiplication. That's right. If we take operation as addition, then meaning of A B inverse means A plus minus B, because additive inverse of B is minus B, means A minus B should be containing H. This is just criteria to be for H is a subgroup. So let us prove. We have to prove in both ways, if and only if, means this is also one type of definition. So suppose H is a subgroup of G. Want AB belongs to H if, or we can say what we want, AB belongs to H, any A and B, then we want AB inverse belongs to H. So how it can prove? Since B belongs to H, implies B inverse also in H because inverse property. And A already belongs to H. B inverse also belongs to H by S1 and 1. So using closure property, we have to show AB inverse belongs to H. So closure property tells that if C and D belongs to H, then CD belongs to H. Product in H. So we get AB inverse belongs to H. Hence proof. Okay. We proved only one part. You can say this is as a part 1. Now we have to prove part 2. What is part 2? Part 2 means given AB belongs to H implies AB inverse belongs to H. And we have to prove H is a subgroup of group G. This we have to prove. Here star is a binary operation, and while we are proving, by default we can take as a multiplication. Means we want to prove 4 properties: closure, associative, existence of identity, existence of inverse. So let's start to prove 4 properties. First we start from note that to prove identity, existence of identity. Why? Because once we get identity, then we can discuss about inverse. And it is, for this, it is useful to prove closure property also. So A belongs to H. H is non-empty. A and second element also take as a A. A belongs to H. So by given A inverse belongs to H. That is E belongs to H. By we can say this is as a B1. So by B1 we get E belongs to H. So identity element exists. Second is existence of inverse. A and E both belongs to H implies E A inverse belongs to H by B1. and that is nothing but the A inverse belongs to H. In this way we proved inverse property. Third is closure property. So we already proved, we start from here, then inverse property satisfy, this is say B2. So by B2 we can say inverse of B means B inverse exists. So A B inverse belongs to H by B1. That means AB belongs to H. In this way we can satisfy closure property. Clearly associativity hold. For associativity we no need to worry about associativity. So in exam also we can write directly associativity clearly holds. So H star is a subgroup of G star. Thanks for listening patiently.